Yeah. Okay. So, pointed out it's all over the world, but it's not just this world. So, I'm going to talk a little bit about C++, but I hope in a little different way. I think C++ rests on a couple of things, and that's why it's survived. It's been predicted dead for the last 40 years, but it hasn't been true. We need stability because a lot of us build software that lasts for decades. And the only guarantee you have that a language works in 10 years is roughly that it's worked 10 years ago. We need to evolve because the world evolves, it changes, we change, and so. And then how on earth do we get from there to here and to the future? And I'm going to talk a little bit about that. And the inspiration of this talk was actually something I was asked to do in Norway last year. I had a group of half academic and half industrial people, and it's really hard to talk to both of those. They have a very different view of things. So I decided to talk about sort of modern C++, contemporary C++, and how we get there. And I'll start by giving a little example, which is not what you usually see with C++. Let's see here, let's see there. There's an example that Alejo gave me from awk. This finds the unique lines of a file and outputs it. And he asked me, how do you do that in C++? And so here is an example of basically a scripting language. First, we grab the whole standard library. Then we bring it into our namespace. Then we start with a hash table, because if you want to find unique things, you can do that. And then we read it line for line, and for each line we see if it's the first one, and if it is, we print it out. And this is not 1980s C++, actually 1985. We didn't name it in 80. And the point about this slide basically is what's not on this slide. There's no allocation, deallocation. If you think that you should use new all the time with C++, you're wrong. There's no sizes. It will work as long as your files will fit in your memory. It's one of those programs. There's no error handling. This is a simple program, and if you don't want, if it doesn't fit, or if you get some dramatically wrong, which I can't see how you do, you'll crash. That's fine for this program. There's lots of programs for which it is not okay. Point here is we have a stretch of goals, a stretch of ideals, what we want to do. There's no code conversions. There's no casts in this. I don't like casts. I once made some rules that says you could only use a cast if you could have a comment and got permission by your manager. That discouraged cast and removed a lot of bugs. There's no pointers. And best of all, there is no use of the preprocessor. The people who built the preprocessor knew it was not great, but they were in a hurry. And it was 1972 or 74, and they had no idea of what we were getting into. We're finally getting rid of that, and it's reasonably effective. It's not as effective as programs that has been tuned for a few decades to do exactly this kind of work. But C++ is tunable. That's very important. One of the points about this talk is write nice code, and if it isn't efficient enough, if there's something else it does, tune it. Okay, now of course just reading in and writing out is not usually enough. So I changed this program a little bit and basically collected all the unique lines in a vector of strings. That makes sense. It's roughly the same program, except I don't need to count because the set will just collect one example of something, and then I make a vector out of the set at the end to output it. That works fine. Notice that the vector's elements are deduced, because of course the elements are the same as the elements of the set, and that's fine. And then I simply can collect lines and output them. And if you're stuck in sort of 20th century C++, this should be shocking. I hope it isn't, but we'll see. So here is sort of going back to what my aims is for C++. That's a sort of a 1980s vintage Bjarne. Basically, the key idea is I want to directly express my ideas for solutions, ideal for what concepts are in the program. I really like static type safety. People sometimes forget that the roots of C++ is C and Simula. Simula was one of the strongest type languages at the time, and I would like to get back to that without breaking the ability to manipulate hardware, which C is good at. Resource safety, I don't like leaks. I mean, you saw the Mars helicopter and the Mars rover. You really don't want a leak so that it crashes. It's really expensive to send a repairman up there. We want performance, aka efficiency, both for manipulating hardware and for running large data centers and doing scientific computations and things like that. And what I call the zero overhead rule is what you don't use, you don't pay for. A lot of languages are designed with the assumption that you will use everything that the language offers, and so therefore you are willing to pay for everything what the language offers. But what if you don't use it? A garbage collector is a good example, and one of the early uses of C++ was device drivers. I want to be able to extend the language basically through abstraction, and I want to be able to afford the result of that. I started out as a young researcher, a student and such. I couldn't afford fancy computers. And I can't talk much about concurrency. That would be another talk or another couple of days or a couple course. But anyway, maintainability. I want to be able to understand the code so that I can maintain it. Platform independence, if that's what you want. I mean, if you don't have the gadgets on the new machine, it won't work. If there's not a MIDI interface, you can't do ordinary music. But without specialized stuff, the standard stuff should be portable, including portability of performance if you can get it. And then stability again, I don't want to break your programs. And one thing that I have observed lately, especially on YouTube and such, is that there's a lot of people who want to show the absolute fanciest, newest C++ and say you should only use things in C++ that's been invented in the last 5 years. That's wrong. Some of the most fundamental and useful in C++ is actually quite old. I mean, classes with constructors and destructors was invented in about the first week in 1979. Exceptions, template, the standard vector, which is the default container until you find a need for something else, so you can use a vector. It can do just about anything. And then there's more recent things that are very important. modules, concept for specifying generic interfaces, lambda expression ranges, smart pointers, you name it. The idea is that you should use what is needed after analyzing your problem and the solution you want to have, and then use a combination of new and old features. There's no prize for using the most fancy latest features. There's a prize for getting a good solution to the problem. So my view is that you measure languages in terms of what you can do with them. It's not an exercise in how to write the cleverest program in 2-column academic format in a paper. There's some examples here about what you can do with C++. It's all done there. I'm not going to say much about AI, but notice a few things here that relate. Underneath a lot of things that you don't see is C++. And here I'll focus on a few things, can't do everything. Resource management, modules, generic programming, and then finally guidelines for how to actually move forward, how to actually use modern C++. And there we drift slightly into research territory, but that's the only thing. The rest you can download and use today. And for the resource management, a resource is anything that you must acquire and then give back later. And you can do that explicitly and implicitly. My philosophy is that you shouldn't require people to give back things implicitly. Ask any librarian, people will take out books and they won't hand them back again reliably. And examples for resources here is memory that everybody talks about, but of course strings and locks and file handles, sockets, thread handlers, transactions. I found some shaders and some graphics library that had to be acquired and give back. So that's what we're talking about. So we want to avoid leaks, and also we want to limit the amount of time a resource is held. I saw some examples where the main advantage of C++ over a garbage collector was simply that it gave resources back twice as fast, which meant that if you relied on a garbage collector, one, you're not sure that it'll be given back ever. Secondly, you use twice as much memory because it doesn't give it back, so you can recycle it early. And the idea here is that every resource is represented by a handle. Resources usually are owned by things like operating systems and such, but there's other systems. And so you have a handle, and that handle is rooted in a scope, so that when you go out of scope, it is automatically released. And so here's the basic idea, nothing particularly new here. We have a vector of t's, and you can construct them with the constructor. I took a constructor of initializer lists of t, and you give it back with the destructor here. There, that's the important thing. So here you raise the level from the basic stuff, pointers and sizes, to something that has proper semantics and possibly checking and nice operations of it. So the first thing on this slide is simply you're raising the level of abstraction one level. And then you build your software, you raise it another level or 3, something like that. And so we can use that, a vector of doubles of some well-known constant, a vector of strings. I parameterized the vector, of course, because I guess only some physicists want just vectors of doubles. Even these days, they like tensors and such. And this works recursively. Here's a vector, a pair of strings and threads. In other words, a pipeline. And the point here is that all the magic in C++ happens right there at the end of the scope. That's where everything is cleaned up, including recursively everything that was held in there. And so, poof, you have cleaned up the stuff right there. There was a competition maybe 10 years ago about what was your favorite C++ feature, and Roger Orr in England won. He sent in that one character there. That's where all the magic happens. Anyway, we need to control lifetime, and we have complete control of lifetime now. We can construct, we destruct, we can copy, and we can move. There's a lot of talk about copying, but only computer scientists would copy to get things from here to there. Make a copy, then move it over there, and then destroy it? No. Even babies can do this. You move it, and that's what we're doing a lot. And so to eliminate copies here, I am simplifying collect strings again, correct lines actually. So we read from the input stream, any input stream, collect the lines and move them up. And basically, if we want to copy the set into a vector, maybe and maybe not, we can optimize that away. Most compilers can optimize the copy away. You can either use a move constructor to get it over out of the scope, or even better, you can simply build that res in the target area. That was an optimization I put in 83. We got copy constructors that guarantees it'll be done, but usually they're optimized away. And so we can reduce that even more. We just have an unordered string, and it copies from input lines and return it out there. And so you got rid of more copying, and the code got simpler, and actually it got more clean. It got more direct expression of what I'm saying. I want a hash table of strings. Unordered set is the C++ standard name for a hash table, and then I turn them into a vector and return them. And that's fine. We've simplified matters. One thing here that you should notice is that there's no line in the standard library. So this code is sort of fake unless there's some more to it, and some more to it is right here. This is classical object-oriented programming, thanks to Christian Nygaard, who invented object-oriented programming. So basically I make a line out of a string and make an input operator for strings that reads for lines that read lines as opposed to just words. Done. Note, conventional object-oriented programming has its place. It is very useful for many things. Just don't think it's everything. I don't want everything in a class hierarchy. I started grumping about overuse of class hierarchies back in at least 82, because I did not want my complex numbers to be members of a class hierarchy. I wanted them to be just like in math. And so finally, we can eliminate more copies. We can move the elements of the set into the vector instead of copying them. So this should be even better. I tested this. It's always a good idea to test your code, and it's always a good idea to measure. And I found that not all standard libraries did a proper move. So if you move the set, it moved the set, it did not move the elements. So here, in some places, you have to put in a perfectly ordinary loop to optimize. But only down here, after having everything else cleaned up, you can tune it as you want. Tuning is important. It's essential for some code, but don't optimize prematurely. Basically, measure before you optimize. I see too many people optimize things without knowing that it actually is necessary. And the key here is to define interfaces that has enough information that you can tune it. You have to have all the type information, you have all the size information, so that if you need to tune things, you can. You have information needed to do that. And that means that you have to well-define interfaces, type-rich code, and that works. My rule of thumb is if I can't understand it, neither can the compiler and the optimizer. This is not perfectly true, but it's true often enough that it's a good rule of thumb. Complexity management, you want to make things simple, and you build with layers of abstraction. And if the layer of abstraction you're dealing with is not good enough, you need to change or tune it for something, you peel off a layer. If that's not good enough, you peel off a layer, and you can work your way all the way down to specialized hardware. And I call that the onion principle, because each time you peel off something, you cry more. You have to write more code, you have more opportunities for mistakes, etc., which is one of the reasons you don't do it unless you have to. Now, one of the hardest things of writing a lot of code is handling errors. In general, don't leak a resource, and if you find an error, make sure that you don't you don't leave any class, any object in an invalid state, and then get out of there. And that's my philosophy about that. So let's have a look here at a piece of code. We have a gadget, and we have a gadget introduced by new, and I see more and more code like that. People have been trained with C# and Java, and they think that if it's a user-defined type, it's a class, you must use new and use the free store and such. But you know, there I make a fairly common mistake. I take the gadget and I put it in a pointer. The pointer is not a resource handle. At least the compiler doesn't know it is, and when I'm reading the code, I don't know it is unless I know the whole thing. And what is inside the gadget, I don't know. It may be holding a lock, it may be having a file handle and things like that. So when we go down here, we may get out of there and we'll leak that gadget, or we may get out of here and we leak that gadget, and unless we remember to put a delete down here, we will leak the gadget there. Now the simpler code here, the local gadget, doesn't have that problem. Doesn't use the free store. It is a resource handle. It cleans up. If it has a proper destructor, which it certainly should have, then done. It all works. The code is simpler, faster, and easier to understand. That's my ideal for design. Interesting. My cursor here seems to have failed. So basically, have an articulated error handling policy. I find that a fair number of programs spend more time in error handling, more code and error handling than it actually does in the business logic or whatever you call it, and I would like them sort of separate. Let me just see if I can. Very strange. Anyway, so basically you use error tests if you know that an exception, that an error is likely. If I open a file, I know that it's possible that the file isn't there, or it doesn't want to open. On the other hand, if I'm accessing memory and I don't know that it's a networked memory, I don't know all the errors in the in the network, and so I should use an exception because it takes care of all of them without complicating the code. Also, exceptions are really good for things when there's no place to return an error code. There's an example there, matrix x equals y plus z. There's no obvious pointers, there's no place to put an error code, so I use exceptions for that. Furthermore, exceptions automatically percolate up to somewhere where you have a chance for handling the error. Otherwise, you get error code hell. You may have 50 tests of all the possible errors going up through the call chain. And here you can rely on what's called RAII. Resource acquisition is initialization, which was the use of constructors, destructors I showed. And basically you look at this code here. It has a vector. It adds some characters to get Dennis Rich's middle initial and name into the DMR down there. There's a thread with that pipeline. Try and write that code with error codes. It at least triples in size, and it more than triples your chance for making a mistake. On the other hand, I have the iStream here I start. I know very well that that file may not want to open, so I test it immediately because I can handle it. There's a lot of rumors about exceptions being slow and large. I recommend the talk there because there's strong evidence that decent exception handling used properly actually is smaller and faster than using error codes systematically. Okay, enough of resources. Another thing that has been bothering me and lots of other people for a few decades is modules. We have include files. Include files are sort of a hack that they put in the early 70s when there was very little in them. Now they're large. There's order dependencies in includes. If you say include A, include B, you may get something different from include B, include A. And that is a source of bugs. It also slows down the compilation because they have to look at all the tokens to recompile. And this is textual inclusion, and it's transitive. That is, if I include A and include, file I got from you, includes C and D, then I get C and D into my namespace, and I may fall over it, and people do. That gives subtle bugs and much repeated compilation. The alternative that we can get now is import A, import B. It's guaranteed be the same as import B, import A. Import is not transitive, so it doesn't leak information out of what you get, and you get only what is said exported from it. Means you can compile roughly once. And so here's an example of the module. It gives better hygiene. It basically cleans up code, are more precise about what you are doing, what you are using, and for that reason the compiler can do a better job. So I want to export, I want to create a module map printer that just prints map. I import a lot of gunk, which you don't want to see, but I need to write my my module using it, and then I export just a single template here, and it prints maps. Okay, it's slideware, but I needed something that fitted on the slide, and it's reasonably real. Basically, a module is a graph with a hash table. In the hash table, you have everything every name that's exported, and they point into the graph. And the graph has all the information needed to, say, generate a template or just bring it out. And so it's very fast. Now, I made that statement and nobody believed me, but there were some tests. Here's one from Daniela Eckert from a really great talk for a couple of years ago. She included a library that her firm had and observed that it was about 500,000 lines of code after pre-processing. Then she put that library into a module, compiled it once, and then brought it back in again. Now it was 5 lines after pre-processing. That's somewhat better. And C++ compilers are actually quite fast these days. I mean, it was a second and a half for 500,000 lines of code. That's pretty good, but it's far too much work. It shouldn't have to work that hard. With modules it doesn't, so we bring it down to 62 milliseconds. And this was a couple of years ago, so your computer today might do better. But there was a 25 times speed up. I don't claim that modules always gives you a 25 times speed up. I've seen it from 0 to more than 100. But I usually, as a rule of thumb, say, how about 7 times? It's enough for me to drink less coffee. I don't have to wait. And then I did a little experiment myself to try and convince people that they could get the whole standard library cheap. And so I did a Hello World program, and it was done in just under a second. And then I imported the STD, the whole STD, everything. And it was a tenth of a second, roughly. That's a factor of 10 for getting at least 10 times as much information available. And I did some more experiments. This is taken from a proposal to the standard committee, and they accepted it, so you can now use it today. I use it for all my small experiments these days. It saves me a lot of work. And again, there's a reference on the slide. I assume the conference will make the slides available. And now to generic programming, which I've been working with for a longish time. In modern C++, generic programming comes from the work of Alex Defner, and it's the backbone of the standard library, containers, algorithms, the concurrency support, memory management, I/O, da-da-da-da-da-da. And basically, it gives shorter, more readable code. It more directly expresses ideas, which is one of my fundamental aims. It has zero overhead abstraction. As a matter of fact, you can do better than zero overhead because it combines information from different sources, making it more available to the optimizers. And it's type safe because the types are usually deduced. And so I can do things like this to saying, I want to sort anything that is sortable. It has a sortable range. And so I can sort a vector of strings, and I can sort a vector of arrays of a size. And importantly, I've specified what the requirements are. It says so on a couple of pages in the standard. You have to have a random access sequence, and the elements of that sequence has to be comparable with less than. And basically, so the implicit thing is what really owns that sequence, what's the type of the elements, what's the number of elements, and what's the comparison criteria. It's defaulting to less than, and you can give your own if you like to. And interestingly enough, if I try to sort a list, I immediately am told that whoa! No, I will not sing. And you should be grateful for that. So you get a list of integers and you try and sort it, and it'll tell you it can't because lists don't have random access. Random access into a large list is very, very slow, and you shouldn't tempt people to do it. So basically, there's three aims for templates. I wanted it to be extremely general and flexible. I was walking around in the late 80s saying it must be able to do much more than I can imagine. And it's obvious. A group like this together has many more ideas than any individual in the group. So it has to be general. Zero overhead, because otherwise the speed fanatics would keep writing with pointers and arrays and making the usual bugs. And I wanted well-specified interfaces to get type safety, overloading, good messages, good error messages. And well, it took me about 20 years to figure out how to get all three. We started with the early versions, and you could sort a vector, you could sort the first half of a vector, you could sort in different criteria, and you could do that for different data types. Good. And this style of programming was very general, flexible, and traditional, as supposed. It was a bit verbose. I never liked writing begin, end all the time. It's not type checked till too late, so the error messages are lousy. But it was close to optimally efficient, and it was successful at a huge scale, because if you don't make mistakes, it runs faster and is cleaner than anything else you can find. And a lot of clever people used it and used it successfully, but it violates one of the fundamental rules of my design criteria. It doesn't specify precisely what it's doing. That is, here you see a template that takes two elements of type, what do I call it? Random access iterator. It doesn't say it's called a random access iterator, but there's no guarantees that it is one. It all works fine if it is, and otherwise you get a bad message. So that's not, it violates. So first we have to start designing what is it that we want to sort. And basically we want to sort a sortable range, and the sortable range is, as I said, a random access range, and it has an iterator that is sortable. Sortable means that it can compare elements and swap and things like that. It's defined in the standard, so we don't have to do it so much. And now I can say I want to sort anything that's sortable. And sortable is not quite enough for what we really want. We want to be able to provide the sort criteria, and so I'm saying a sortable range is a random access range that is sortable with the compare criteria. And now we have precisely specified what the sort template is, and actually more than that. And one thing, by the way, to point out here is that concepts can take several arguments. They're not types of types. They're basically functions, compile time functions. And the use here, I can sort a vector, and I can try and sort a list, and I get a decent error message as, well, not as usual, but as it should be. And overloading can be based on concepts. So here I am, what am I doing? Oh, I am sorting the traditional way. We have to have compatibility. We don't want to break billions of lines of code. So I define a sortable iterator that you don't have to take the whole range. You can define the sort with the begin and the end as usual, except that it gets properly checked. And so now the old stuff works also. And it is in the standard, so you don't have to do all of that. Concepts are functions, compile-time functions that can take types as arguments. And you can also you usually define them by calling other functions, other concepts. But you can also build them straight out of language facilities. That was the bit that was missing in the 80s and 90s. We didn't know how to do that. People were putting in things equivalent to function pointers and v-tables, type classes, things like that. And you got indirections, and the thing that modern hardware doesn't like is indirections, especially not indirect function calls. So we can specify things by use patterns. Here I'm using an example, equality comparable. If you have a T and a U, you can compare them if they have less than, have equal and not equal both ways. Fine, you can do that. And if you want to test it right up front, you can do that with static assertions in modern C++. Equality comparable int and double, yeah. Equality comparable integers, integrate, yes. If T and U is the same, of course you can do it. And it is not equality comparable with int and strings because we don't have implicit conversions from strings to integers, and that's the way at least some of us wants it. We've always had concepts. This is the interesting things. We've just invented a notation for something we've had all the time. C has built-in types, arithmetic and floating. You can look up in the first writings of Dennis Ritchie. They're there. They're just not something that the compiler can understand. It's just us. The STL concept, iterator, sequences, containers, we've had them. And we can go back further. Math has monad, group, ring, etc. for a couple of centuries. And I tracked down the graph concepts, edge, vertex, graph. We have them since 1736. We may have them earlier, but I found the bridges of Königsberg, which is the first place I've found them. So C++ concept is simply a notation that the compiler and we can understand. And the benefits, good design, reliability and maintainability, massive improvement in error messages, and overloading, which is important. And you can simplify design. Here's an example of writing a smart pointer type that that simply says that you have an arrow operator if and only if you are pointing to a class. And I have a class pair, which you can take one kind of pair into another kind of pair, provided you can convert the source into the target. If you think that is trivial, it is. If you think it's trivial without concepts, look in the standard, it is horrendous. So this is an example of compile time programming. Any sufficiently function can be evaluated at compile time. And this is the closest thing C++ has to pure functions, which are very good for correctness checking and such. There's an example. I got this request from a Japanese embedded systems programming. They wanted they wanted integer square root, presumably because they had to compile distances, and so we can now do it. We just stick a const expr or a const eval in front of a function, and the compiler will check that it can be compiled if you give it compile time known values, and so it works. You don't have to work this on your doodle pad and potentially have it run. And it doesn't just work for built-in types, it works for user-defined types too. I have an example there. Is the what's the weekday of Christmas Eve in 2024, it will calculate that at compile time, which means it's blindingly fast because there's no computation at runtime. And does it matter? Yeah. I haven't seen resource leaks after basic testing for years. I once redid a critical production program that has been used more or less successfully for 20 years, but there was some bugs that needed to be removed, so I removed them with friends, with a team. And the key technique was to simplify it, and we got a major surprise. Once we'd thrown away all the complicated stuff, it ran 100 times faster. You can't expect that all the time, but sometimes modern C++ gives you a benefit, apart from being able to read it. And it's widely applicable. I would like to talk about concurrency, but I don't have the time, so apologies for that. You can find it in the standard and support it, and there's endless talks about it. And now, how on earth do we get to the 21st century? We have billions of lines of code, and they're written in the old style, and we know we can do better with modern styles, but how do we get there? Old habits die hard. We carry we carry old ideas around in our heads, and one of the more dangerous things in hardware is we can't change the language because we've tried a few times with deprecating features and such. There's always somebody that complains. People always give the challenge to me in the standards committee. We want C++ to be simpler, it's too complicated. Yep. And by the way, while you're doing it, add 2 features here. I absolutely need them yesterday. And whatever you do, don't break my code. You can't do that. That's a trilemma, if such a word exists. And we have to do something else. So we can't change the language. We've tried. We can change the way people use the language. That goes from guidelines and then enforced guidelines. That's what we want. So we have guidelines, they're available now, things like the C++ core guidelines that I've been working on with others for years, and profiles, which is working their way through the standards committee, which is basically enforced guidelines, so that you can basically say, I want type safe C++, or I want no memory leaks in C++ and dangling pointers and things like that. That you can get. Also, I have educators saying I want to make sure my students don't use sort of 1994 C++. So you can do that. So basically this works on the idea of a subset of superset. People want a subset of C++, but they don't want to lose the facilities they use to build their abstractions. So basically you build the abstractions out, and then you remove the stuff that is error prone or you don't want for some reason or other outside the implementations of those abstractions. So basically I tend to use things like vector and smart pointers. That's an extension. Spans, it's an extension. And once you have those, you don't need actually subscripting pointers. So you can ban that. And you can do that today. So the core rules here. These are the core rules that you can start aiming for, but you can't get them immediately because you have a lot of old code. I mean, if you're starting with something from scratch, you can get there. You can just do it. But if you have 1 million lines or 500 million lines of code, you have to go gradually do it part of the system from part of the system. But the core of the core, no initialized variables, no range or null pointer violations. That takes runtime. Checking means you have to use a hardened standard library. They exist. Everybody, all major suppliers have them. It's just there's no standard way of asking for them. I'm trying to get a standard way of asking for them. No leaks, no dangling pointers, no type violations, through pointers, and no invalidation. So basically, here's an example of how not to subscript pointers. There's a lot of interfaces that are of times. There's a pointer and a size, and you use them. But the point is that we don't actually know that the pointer of the size match. So if you have something down there, that's a bug. My finger slipped, and I got 1,000 instead of 100. But if you build a type called a span, that really is the abstraction of a pointer with a side of the elements it's pointing to, you can write simpler code, and violations stand out like a sore thumb for static checking or for code reviews. And you can deduce things. So if you have an array of 100 elements, you can simply say, I want a span for that array. It builds the thing, and then the span in the GSL, the Guideline Support Library, does range checking, and you just can't make a range error there. Unfortunately, the standard didn't guarantee the range checking by default. You can ask for it, but you have to ask for it. That's a mistake. Invalidation is a trickier thing, but again, we can handle it. There's a vector of 2 elements. I grab the pointer to the first element, then I call a function that happens to expand the vector. Now the first element may or may not point to the first element, because there might have been relocation done there. We just have to catch that. That is a static analysis problem. It can be solved. It has been solved. There's some libraries, there's some papers there describing how. And so I suggest an initial set of profiles for the standard. I have been around talking to people asking what kind of guarantees do you want? And it is not just memory safety. It's a lot of things. Ranges for algorithms, over and underflow, casting. We can basically ban. Now we have good generic programming. There's another talk about that. You can find it on the web. Generic programming using concepts. Concurrency, eliminate deadlocks and data races. That's really hard. I don't have a complete design for that. Initialization, invalidation, pointers, ranges, resource management, Parts of all of this exist. Complete doesn't exist, and guarantees doesn't exist, though there's a framework coming out that allows you to ask for it, and I hope it's in the next standard. It's a big mistake that it wasn't in the C++ 26 standard. And so basically, here's the C++ model: static type system, systematic and general resource management, efficient object-oriented programming. I'm not saying it's bad, outdated and such. For some places it's just right. Flexible and efficient generic programming. It's now reasonably complete in C++. A lot of compile time programming. I was told it was useless and unimplementable. It is all over the place now for performance and correctness. Direct use of machine and operating system resources. It is a systems programming language, among other things. Concurrency support, and we need to get rid of the C preprocessor. And so here, back to what I said in the beginning. What matters is what you can build with all of this, not how clever or elegant it is when you write a paper. And we have some successes at a fairly large scale there. C++ has evolved. It was designed to evolve. And well, there's a history graph. I'm not going to go into details for that. has a bunch of references if you get this paper, and then I will switch to the Q&A now. I promised the conference I would be 10 minutes over the 45 minutes allotted. They said okay. I almost made that.